So now that we looked at valves and how we control flow to a different part of the circuit, now let's do something with the flow. So we got this fluid power, we've directed it to where we want it to go. Now we want to make something happen with it. And there's really two fundamental kinds of actuators that do things. And again, primarily we're looking at either rotational energy, rotational power to rotate some machine, or we're going to have linear power where we move something linearly. And we've already talked about actually the motors, so I won't spend any time with them here. So they're, again, basically the same thing as pumps. Functionally, they're the same. The efficiencies go on the opposite side, so you got to remember that, because the input to a motor is the fluid power, the output's the mechanical. Whereas the pump, the input is the mechanical and the output is the fluid. So just keep that in mind. But let's take a little bit closer look at some cylinders, different types of cylinders, and there's a lot of different kinds that we can purchase to do different things. The very simplest kind that you see on the lower left there is just a piston that comes out. So we can put fluid into the left-hand side, as you see the drawing there. As we put fluid in the left-hand side, that's going to cause that thing to extend. We can actually bring fluid in from the right-hand side to cause it to retract. So we'll talk about the extension and retraction. And so this way would be extension. And coming back in then would be the retraction. We use that pretty often. So again, oil comes in here, the fluid comes in here, pushes it out, fluid comes in here, pushes it back. Okay, and here's what the JIC symbol looks for. It's pretty descriptive of what's going on. And the fundamental relationship, force equals pressure times the area. Okay, so our pressure, you think of pressure as force per unit area, and that's what we have. So how much force we can develop is how much pressure we have in the cylinder and what area it's acting over. Now we'll see that we have two sides of this cylinder, and those forces have to balance out. We'll come back and look at that later. So here's some examples of cylinders in action. And you can see linear cylinders on top of this articulating arm up here. There's a cylinder that would cause this thing to tilt out, so there's several cylinders on that. There's one black one right there, one on top, one here. So all these will cause the different motion there. Now I show this picture is kind of neat because this orange part on the machine on the side is what we call a rotary cylinder. So a lot of us are familiar with these linear cylinders, linear hydraulic cylinders, but there is such thing as a rotary cylinder, and it's shown here in the cross section, so looking down on it from the top. So it's basically just a vane or a wiper that wipes around or swings back and forth here. So this one has looks like about a 270 degree or maybe a little bit more range of motion. And in this particular application, this makes a lot of sense because this arm would have to swing back to the tractor, but we don't need that arm to swing 360 degrees. It can't go past the tractor cab. If we swing it forward, it can't go in front of the tractor. So we have a limited range of motion. So we can use a cylinder like this. We put fluid in one side, it pushes the vane around. If we put fluid in the other side, it'll push this vane back. So it'll control the swinging motion of this. So just show you something a little bit different there. But let's look at some calculations on this. Pretty again, there's lots of different options here. Drawing showing a spring return, so we can have fluid coming in, a spring return on it. Here's one that we were just looking at, where we have a double acting cylinder with fluid coming in, and then we can push fluid in the backside and retract it. We could actually have single acting cylinders that don't even have this retraction connection on it. So it would only extend, and then we would rely on gravity or whatever load we're lifting to actually return it. So a good example of a cylinder like that is the one here on this big dump truck, where we're trying to lift this bed to be able to dump the load out of that truck. A couple things going on here. This is single acting. All we got to do is push it up. Gravity will bring that down easy enough. But the other thing we have going on is look how high we need to lift this. And if we had to use a cylinder that would have that range of motion, a regular cylinder, this thing would have to be really, really tall. It would be way too tall to put on the truck. So what we do is use a telescoping cylinder. So you can see there's different diameters of the different sections of the cylinder coming up there. So as we lift this thing, we put fluid in the bottom, it's going to push each stage out sequentially. And well, obviously, when the first stage is going out, we have the most cross-sectional area. So you think of the pressure here acting on the bottom of that. It's acting on the bottom of all of those sections, and so we have a relatively large cross-sectional area. So that'll lift a heavier load. When we start getting extended out, we only have the pressure, the last section or two, we only have the pressure acting on a much smaller area. So the force that it can develop is a lot smaller. And in this particular case, it makes sense. And you could do the statics on this and think about this. So when this bed is laying flat, the center of gravity is pretty far forward here. It's halfway between the cylinder and depending on how the load is on the wheels. But as we lift it up, the moment arm gets shorter, so the center of gravity of load gets closer to the back wheels, transferring more weight on this back pivot, which means there's going to be less weight that I need to push with the cylinder. So hey, that means I don't need to push as much, and so the telescoping cylinder will help me out. It also helps me out to keep from lifting heavy loads too high. So we'll do this on forklifts, for instance, so that if I got a load on a forklift, I can lift a pretty heavy load to a certain extent, but once I start getting to these subsequent sections up here with a smaller diameter, now I can't lift as much, and that keeps me from lifting loads that are too heavy, too high in the air to increase the stability of the vehicle. All right, so let's look at a cylinder here. Let's say that we've got an example, and I'll just go ahead and draw a cylinder over here. We'll throw some numbers on it. So very, very simple cylinder. I'm going to stick a load on the top of it, like that. So there's your statics class. We always draw the weight that's shaped like that and write the number in and how big it is. But there's my two ports coming into that, one to extend it and one to retract it. So I'm going to hook this up to a tractor, and I'm going to extend this cylinder. So I want to know what force can I lift. Okay, so for my particular tractor, let's say that for my example, and we'll use the English system this time just to be kind of different. So let's say that my tractor can develop, 2,800 PSI. So that's what it can develop. The cylinder is a 4-inch diameter. But I'm going to give you another piece of information that we got to remember. I'm going to give you the rod diameter. So it's a 1-inch rod diameter. So what that means is cylinder diameter, that's this diameter of the overall piston here. So this is 4 inches, this diameter is 4 inches, but this diameter, the diameter of the rod, and we show it on the drawing as a line, but it actually does have a dimension. This is 1 inch. So the diameter of the rod is 1 inch over there. Now why does that matter? Well, I'm also going to tell you that my tractor, I can develop 2,800 PSI going into there, but I'm going to connect this up to the return port, so I'm actually going to have flow coming back from this thing, going back into the tractor. But when it goes back into the tractor, and we'll see this in the lab when we test a tractor, you may have already seen it, that there's probably a filter, there's some valves, there's whatever in the tractor to get this before this fluid can get back into the reservoir. So it's going to be some resistance to this flow. So we talk about this as being the back pressure. So we have 2,800 PSI available here to lift the load, but when that thing is moving, we're going to have 500 PSI over here. So 2,800 down here, 500 PSI back there resisting that. Oh, so if I've got pressure resisting the motion of that, that's going to limit what I can lift, because I've got this pressure down here creating force up, but I also have the back pressure that's creating a force down. That force down is going to be acting over a different area because the rod is taking up some of that area. So if I look at the cross section, look at the end view of that cylinder. So this is my 4-inch cylinder, but my rod is in the middle there. So the area on the back side of the cylinder is basically everything except the rod. So it would be that area there. So I take the area of the cylinder and subtract out the area of the rod. So my equation is going to look something like this. The force that I can develop is equal to the pressure, and I'll use subscript 1 because that'll stay consistent with what your book does. So P1A1 minus P2A2. All right, so this is side 1 down here. The extension side we talk about as side 1. The retraction side we talk about as side 2 up on top. So I need to know the area of 1. So I like to calculate the areas first to keep my Equation is a little bit simpler. So A1, we said this is a 4-inch cylinder, so this is just pi d squared over 4, so it's pi times 4 squared over 4, and that gives me an area of 12.56 square inches. Area 2, that's the back side of the cylinder. What I have to do is take the area of the whole piston, subtract the area of the rod. So area 2 is going to be this 12.56 square inches, subtracting off pi times 1 squared, because that's the diameter of the rod, over 4. And that equals, if you run the equation, 11.78 square inches. All right, so what force can I develop? So the force that I can develop is equal to pressure on side 1, which is 2,800. PSI, let's write that out. What is a PSI? It's pounds per square inch times my area, A1. What is A1? That's the 12.56, so times 12.56 inches, square inches. The inches cancel off and I end up with pounds, okay? So that's what force I have developed by pressure 1 on side 1 of the cylinder to try to extend it. But I have this back pressure on it. So the back pressure is the 500 pounds per square inch times the area 2, the area of the backside, which is smaller. So this is 11.78 square inches. Square inches cancel off. I'm left with pounds, so I'm subtracting pounds from pounds. So that works. And so just for perspective, I'll write these numbers out. So this one becomes, the force there is 35,168 pounds is what it could develop without the back pressure. But the back pressure is going to take off about 5,000 pounds, 5,890 pounds. So the overall force that I can lift is 29,200. Okay? So again, how do we interpret that? We would be able to lift 35,000 pounds if we didn't have back pressure, but since we have the back pressure, that's going to take away a little, almost 6,000 pounds of lifting capacity. So what I can really lift then is 29,200 pounds. Okay, so that's how we get the force on it. That's really simple. You guys as engineers should be able to handle that. The other interesting thing that we look at is the velocity, and I'll just write this equation down, but you guys can figure this out, and this is real simple math as well. So if I want to know how fast that cylinder is going to go, I basically look at what volume I have to displace here. So if I look at the flow rate coming into the cylinder, that's going to be so many gallons per minute or liters per minute or whatever. How many liters does it take to fill this thing up? So how fast will this fill up and how fast will it move this? And so the equation would look like Q divided by A. So we're basically taking the volume divided by the area, end up with a linear length per unit time, and that then is the velocity. That's how fast that cylinder would move. So easy ways to get the force and also to be able to calculate the velocity of the cylinder. So that's the other common actuator. Pretty simple to do the calculations there, and we'll obviously get some practice doing this.